Welcome, folks, to lesson 14. Today we're going to talk a little bit about antiderivatives and indefinite integration. These are topics that I believe you've discussed before, so this should be kind of a review and something that's, I think, fairly light for a Friday. So let's get down to it. Antiderivatives, okay? Just a common definition for an antiderivative, basically, more of a formal definition. It says that if big F is an big F function is an antiderivative of your regular function if on that interval I, big F of prime of x, the derivative of that antiderivative, gets you back to your original function. Okay, so what integration is it's kind of the inverse of differentiation. It's kind of the reverse process. You're undoing the differentiation processes that you had went through and learned the previous couple of chapters. To take an integral, right, what you need to do is increase instead of decreasing, instead of multiplying your exponent out front, right, instead of going through and multiplying, instead of multiplying your exponent, and I'll abbreviate that, right, instead of multiplying your exponent and then lowering and then subtracting 1 from your exponent, right, the inverse of that, right, working backwards, if you're going to work backwards from that, is you're going to add 1 to your exponent. Okay, you're going to add that 1, and then after you add 1 to your exponent, you go through and instead of multiplying now, you divide by your new exponent. Okay? So an example of that would be something where you had, say, for instance, you had the integral of 2x to the third power. Okay? What you're going to do is you're going to increase the exponent by 1 and then divide by that new exponent. Okay, so you're going to increase it, right? And then you're going to divide by the 3 plus 1, which is 4. So your antiderivative basically is going to be a function, or better yet, a set of functions, such that when you take the derivative of them, it gets you back to your original. So the derivative of 1/2 x to the 4th is 2x to the 3rd, but now that isn't, there's a lot of functions that when you take the derivative of them give you a function 2x to the 3rd. Say 1/2 x to the 4th plus 1, 1/2 x to the 4th plus 15, 1/4 x to the 4th, minus 2,000, any one of those functions. So we include this constant c, and usually that has a name. It's called the constant of integration. So in general, if we take, if we go through and we can work backwards from the derivative, right, to the integral, right? Here's the integral, right? And then, if we work backwards from that, we can take the derivative of x to the n and get that. So, the reverse processes. Now, there are some names, such that when we take the integral of something, this is the indefinite integral. Notice there's no boundaries right here. There's no bounds that we're taking the integral between. Normally, this function right here that you're taking the integral of is called the integrand. This right here, this dx, specifies the variable that we are integrating. Normally, what we call this dx is what's called a differential. Okay, and we really haven't talked about that, and there's not much of a need to talk about that right now. But that's what it is. It's this slight little differential dx in there, and that'll make a little bit more sense, right? When we talk a little bit about area. Okay, and then this big F of x is your antiderivative, and then your c is what's called your constant of integration. Okay, and that's always going to be included when you're taking indefinite integrals. You have to include that. That's a must. Absolutely must have that in there. Okay, so never forget c. Okay, always include that. Right. The next thing is a couple of common integration formulas. The integral of 0 is just the integral or antiderivative of 0 is just a constant. And that makes sense because when you take the derivative of a constant c, you just get back to 0. The antiderivative of some constant, say k, that's not 0, okay, is just k times x, right? Because the integral basically of k, right, you can think of this as basically being kx to the 0. And then when you take the integral of that, you up this right here to 1. So now you have x to the 1. And then when you divide by 1, right, it's just basically k x. And then don't forget your constant of integration. Okay? Now, k times, if you have k times a function, some constant times a function, I usually take the constants out when I integrate them, unless it's doesn't make much difference. But a lot of times, if I possibly can, I'll rip the constant, a constant outside of the integral, just to make sure that it's a little bit we're concentrating on just maybe the function itself, and not worrying necessarily about the constants. Just like in differentiation, the integral of the sum or difference of two functions is the sum or difference of two distinct integrals of those functions. All right, and then the integral, of course, of some power of x, we just increase the power by 1 and divide by the new exponent. Notice this works every time, with the exception that n is equal to -1, and we'll talk about that when we get to that section. It's more going to be on natural logarithms. Okay. Some common trig functions that you're going to want to know the antiderivative, just like your differentiation. You're going to want to know the formulas for your trig. You got to know them. The integral of cosine is sine. That makes sense because the derivative of sine is cosine. The integral of sine is minus cosine. Okay, that makes sense because the integral of cosine is negative sine, and then the negative of that is positive sine. The integral of secant squared is tangent. That makes sense because the derivative of tangent is secant squared. The integral of secant tangent is secant of x, plus c, of course, on every one of those. The integral of cosecant squared is going to be negative cotangent. And that makes sense because the derivative of cotangent is negative cosecant squared, and the negative of that is cosecant squared. And finally, the integral of cosecant cotangent is going to be negative cosecant of x plus c. Okay? So those are some main integrals that you're going to want to know, that you're going to want to have down pat. Okay, cold. Representation of antiderivatives. Usually we give antiderivatives kind of a capital letter, but that's, it's kind of the normal routine, kind of notation. So if f is the antiderivative of little f of x on an interval I, then g is the antiderivative of f on the interval I if g is of the form big F of x plus c. So g is just the antiderivative, basically. F is a distinct antiderivative, right? And g kind of encompasses all the antiderivatives, all constants of constants added to f of x right here. Okay. Kind of some basic rules right here when taking the antiderivative. You can take the constant out. You don't have to. What I do is I just up the power by 1 right here to go 2, and then we, divide by 2. So I go through, I up the power by 1 right here because the power of this originally is 1, right? We up it by 1, divide by 2, and so we get 3 halves x squared plus c. Okay? And you can do that all the way through, no matter how many deals you have in there. It's very helpful. It's very helpful, just like in differentiation, when you're going through and doing these things to rewrite them. So now, normally when I have a function where it's got like just constant term right here and the constant term right here with a constant term over something x to the third. Sometimes helpful to write it in terms of a negative exponent, right? And then you can go through and take the antiderivative of that. Up it by 1, if you add 1 to negative 3, you get negative 2, and then dividing by negative 2 right there, plus c, you have your antiderivative. We just write it a little bit nicer in this form right here, and you're done. Just like in differentiation, your radicals, I would write them in terms of powers. So write the powers. So the square root of x is the same thing as x to the 1/2. Then upping that exponent by 1 and dividing by 3/2. Okay. So if I divide by a fraction, normally I don't think about dividing by 3/2. I just multiply by its reciprocal, right? And the reciprocal of 3/2 is 2/3. And then it's 2/3 x to the 3/2, or better yet, 2/3 square root of x to the third plus c. Okay. An example right here, if we got a derivative and we want to find the antiderivative of that whole thing right here, we can do that piecemeal by going through and taking the antiderivative of 5x to the 4th minus the antiderivative of 3x cubed plus the antiderivative of 7x squared plus the antiderivative of 10x minus the antiderivative of pi. Now, you don't have to write all this distinctly out, but that's what basically you're doing. You're taking the antiderivative of each individual part of this polynomial. And the antiderivative of x to the 4th, we up this by 1 to get 5, and dividing by 5, we get x to the 5th. Same thing with 3 minus 3x to the 3rd. We take the antiderivative of that. We add 1 to the exponent and then divide by 4 to get 3/4 x to the 4th. And then with the 7x to the 2nd, we go through on that, right? And we add an exponent of 3. We add a 1 to the exponent and then divide by the new exponent 3 to get 7/3. And similarly with the 10x to get 5x squared, and the pi to get pi x, and then make sure, of course, always to include your plus c on that. Okay? Sometimes they will want you to find a particular solution, right? And when we're finding the particular solution right here, let's say that we have the function f of x equals 1 over x squared. right? And if we want to go back and we want to find a particular solution, maybe this is f prime or whatever, right? Maybe this is f prime, better yet. Then in order to find what f of x is distinctly, right? We integrate both sides right here, right? With respect to x. Okay? We integrate both sides with respect to x, and then, right, we integrate that. Integrating x to the 1 over x to the second is the same thing as integrating x to the negative second, which is x to the negative 1 over negative 1, or negative 1 x plus c. Now that is your general, this is what's called your general solution, right? It's not a particular solution at all, right? This is your general solution, right? So this guy is, in general, your solution because it's got a plus c right there. But now in order to solve for that, we need this initial condition in order to get a distinct function, right? And so it says f of 1 is equal to 0. We go through and solve for that. We solve for our c right here. We substitute a positive 1 in for x, and we get a negative 1 plus c is equal to 0, or c is equal to 1, and that means our particular solution is this guy right here. And we'll talk more about particular solutions and things like that when we get to differential equations in a little bit. Your assignment for today, okay? I want you to go through, I want you to practice on your antiderivatives, okay? Practice on those antiderivatives, get pretty good at those, because we're going to be using a lot of those this year, especially when we get into Chapter 8 and Chapter 9. So it's going to be important that you're able to do those very, very well. Assignment starts on page 255 and 256. I want you to do 15 through 43 odd. Okay? Just the odd ones on those. All right? And if you've got any questions, please let me know. Okay? So let's see here. There we go.